Hi, my name is Mahsa Sarabi and I'm presenting my project on emotion detection using facial recognition with real-time camera. A huge part of our communication is nonverbal. Our faces are a universal language conveying a rich spectrum of emotions without a single word. Now imagine if our technology could understand this language. This is the goal of facial emotion recognition or FER, a field of AI that aims to automatically interpret human emotions from images. The goal of this specific project was to design and build a system that could do this accurately and most importantly in real time. But why this is so important? The applications are vast. In human-computer interaction, it can create more empathetic AI assistant. In mental health and medicine, it can help monitor patients' emotional state. In marketing research, you can detect people's emotion during the buying a thing or doing the stuff. In automotive safety, it can detect a driver's distraction. This technology has the potential to make our interactions with machines safer and more natural. We have seven main emotions that we want to detect: sad, angry, surprise, neutral, fear, disgust, and happy. In the most articles they use CNN. So first of all, I use simple CNN, but we have so much overfitting. So I try to use a classic form of CNN named VGG16. So many articles use these architectures and try to improve the accuracy. It's a powerful but heavy model, extremely slow and large. It has 130 million parameters, so it's not suitable for real-time application, and it may cause overfitting on a smaller data. As you can see from these training curves on the right hand, VGG16 also suffered from severe overfitting. The validation loss, shown in orange, begins to increase after just a few epochs, which is a classic sign that the model is memorizing the training data instead of learning to generalize it. This, combined with the slow performance, made it unsuitable for our real-time goal. And also, each time I try to edit the parameters and see the results, it takes so much time, so I try to not use it. And I see some of the articles that use MediaPipe for extracting the features from the main dataset. I use it too, but because of the low quality of my dataset, it fails to detect faces, so I try to not use it. Before I'm telling the main architectures, I want to explain about datasets. At first, I use FER 2013, the open source datasets, low quality grayscales datasets. I have so much overfitting because of the low quality and also unbalancing the images in each file. So I try to use other dataset that has more qualified. It's rough DB. It has high quality, but it has so much unbalancing. For example, for the feeling of happy, it has 4,000 images, and for feeling of the um, fear, it has just 400 images. And with the data augmentation and other stuff, I can't improve it. So I request a dataset named KDEF. It has balanced classes from 70 individual, 35 men and 35 women. It has 7 emotions, and from 365 angle view as you can see in the pictures. For pre-processing, we have two main steps: data splitting and data augmentation. For data splitting, we use group shuffle split grouping by subject ID to create our train and validation sets. I don't have test sets because my data is so much less, so I try to use this group shuffle split to separate the validation and train sets and make sure that the train parts won't see any of the pictures of the validation sets. And with this group shuffle split but grouping by subject ID, it's a critical step to prevent identity leakage and ensure a fair evaluation. For example, every pictures of the person number one, if they are in training set, it won't be in any of the pictures of this person, won't be in validation set, and vice versa. And yeah, for the step 2 data augmentation, I use random flip, random rotation, random zoom, and random translation. For our architecture, we use the efficient net B0 model with transfer learning. We implemented a strategic two-stage training process. In stage 1, we froze the pre-trained base. We download the pre-trained weights and use this for transfer learning. We froze this pre-trained base and trained only our custom head classifier. This is a safe way to adopt the model without destroying its learned feature. As you can see, it got us to 37%. It's for head training, and for fine tuning we have to unfroze the top layers of the base model, and the top layers of the base model is for minor features. And because EfficientNet B0 has 213 layers, we unfroze the last 13 layers, and then we fine-tune it, and we got final validation accuracy to over 85%. And we use callback and early stopping too, and if the validation accuracy won't come up enough, it would be the training would be a stop, and it use the best weights for the training. And for real time, use OpenCV and MediaPipe 2 for detecting the face, the eyes, and these stuffs. Now for the result, our final model achieved an overall accuracy of 85% on the unseen validation data. This classification report gives us a more detailed breakdown. The model shows excellent performance on distinct emotions like happy and disgust, with F1 score over 19. However, the key challenge, as shown by the low recall of 5500 for the fear class, was in distinguishing more subtle or similar emotions. And to understand why the model struggled with fear, we can look at the confusion matrix at the left hand. You can see for the emotions of fear, it can detect wrong the emotion is with feeling of the surprise because of the form of the eyes and the mouth. During both emotions, they are similar to each other. And we can see the most emotions it detects right. And here is the real-time test. It's neutral, happy, sad, disgust, fear, angry, and surprise. And we successfully developed an efficient real-time FER system. We achieved the final accuracy of 85%, And the hybrid approach, the efficient net and also media pipe, proved to be very effective. For future works, we want to work with in the wild dataset. In the wild datasets are the dataset that recorded in a real world with real emotion, not in laboratory with actors. Thank you for your attention.